The scientific method is a body of techniques for investigating phenomena, acquiring new knowledge, or correcting and integrating previous knowledge. To be termed scientific, a method of inquiry must be based on empirical and measurable evidence subject to specific principles of reasoning. The Oxford English Dictionary defines the scientific method as a method or procedure that has characterized natural science since the 17th century, consisting in systematic observation, measurement, and experiment, and the formulation, testing, and modification of hypotheses. The chief characteristic which distinguishes the scientific method from other methods of acquiring knowledge is that scientists seek to let reality speak for itself, supporting a theory when a theory's predictions are confirmed, and challenging a theory when its predictions prove false. Although procedures vary from one field of inquiry to another, identifiable features distinguish scientific inquiry from other methods of obtaining knowledge. Scientific researchers propose hypotheses as explanations of phenomena and design experimental studies to test these hypotheses via predictions which can be derived from them. These steps must be repeatable to guard against mistake or confusion in any particular experimenter. Theories that encompass wider domains of inquiry may bind many independently derived hypotheses together in a coherent, supportive structure. Theories, in turn, may help form new hypotheses or place groups of hypotheses into context. Scientific inquiry is intended to be as objective as possible in order to minimize bias. Another basic expectation is the documentation, archiving, and sharing of all data collected or produced, and of the methodologies used so they may be available for careful scrutiny and attempts by other scientists to reproduce and verify them. This practice, known as full disclosure, also means that statistical measures of their reliability may be made. Overview. The DNA example below is a synopsis of this method. Ibn al-Haytham, Al-Azan, 965-1039 Iraq. The Arab scholar who is considered by some to be the father of modern scientific methodology due to his emphasis on experimental data and reproducibility of its results. According to Morris Klein, modern science owes its present flourishing state to a new scientific method which was fashioned almost entirely by Galileo Galilei. Dudley Shapiro takes a more measured view of Galileo's contribution. Johannes Kepler, 1571–1630. Kepler shows his keen logical sense in detailing the whole process by which he finally arrived at the true orbit. This is the greatest piece of retroductive reasoning ever performed. C.S. Peirce, c. 1896, on Kepler's reasoning. Through explanatory hypotheses. The scientific method is the process by which science is carried out. Because science builds on previous knowledge, it consistently improves our understanding of the world. The scientific method also improves itself in the same way, meaning that it gradually becomes more effective at generating new knowledge. For example, the concept of falsification, first proposed in 1934, reduces confirmation bias by formalizing the attempt to disprove hypotheses rather than prove them. The overall process involves making conjectures, hypotheses, deriving predictions from them as logical consequences, and then carrying out experiments based on those predictions to determine whether the original conjecture was correct. There are difficulties in a formulaic statement of method, however. Though the scientific method is often presented as a fixed sequence of steps, they are better considered as general principles. Not all steps take place in every scientific inquiry, or to the same degree, and are not always in the same order. As noted by William Whewell, 1794–1866, invention, sagacity, and genius are required at every step. Formulation of a question. The question can refer to the explanation of a specific observation, as in why is the sky blue, but can also be open-ended, as in how can I design a drug to cure this particular disease. This stage also involves looking up and evaluating evidence from previous experiments, personal scientific observations or assertions, or the work of other scientists. If the answer is already known, a different question that builds on the previous evidence can be posed. When applying the scientific method to scientific research, determining a good question can be very difficult and affects the final outcome of the investigation. Hypothesis. An hypothesis is a conjecture based on knowledge obtained while formulating the question that may explain the observed behavior of a part of our universe. The hypothesis might be very specific, e.g., Einstein's equivalence principle, or Francis Crick's DNA makes RNA makes protein, or it might be broad, e.g., unknown species of life dwell in the unexplored depths of the oceans. A statistical hypothesis is a conjecture about some population. For example, the population might be people with a particular disease. The conjecture might be that a new drug will cure the disease in some of those people. Terms commonly associated with statistical hypotheses are null hypothesis and alternative hypothesis. A null hypothesis is the conjecture that the statistical hypothesis is false, e.g., that the new drug does nothing, and that any cures are due to chance effects. Researchers normally want to show that the null hypothesis is false. The alternative hypothesis is the desired outcome, e.g., that the drug does better than chance. A final point, a scientific hypothesis must be falsifiable, meaning that one can identify a possible outcome of an experiment that conflicts with predictions deduced from the hypothesis, otherwise, it cannot be meaningfully tested. Prediction. This step involves determining the logical consequences of the hypothesis. One or more predictions are then selected for further testing. The more unlikely that a prediction would be correct simply by coincidence, then the more convincing it would be if the prediction were fulfilled. Evidence is also stronger if the answer to the prediction is not already known, due to the effects of hindsight bias. See also postdiction. Ideally, the prediction must also distinguish the hypothesis from likely alternatives. If two hypotheses make the same prediction, observing the prediction to be correct is not evidence for either one over the other. These statements about the relative strength of evidence can be mathematically derived using Bayes' theorem. Testing. This is an investigation of whether the real world behaves as predicted by the hypothesis. Scientists and other people test hypotheses by conducting experiments. The purpose of an experiment is to determine whether observations of the real world agree with or conflict with the predictions derived from an hypothesis. If they agree, confidence in the hypothesis increases, otherwise, it decreases. Agreement does not assure that the hypothesis is true. Future experiments may reveal problems. Karl Popper advised scientists to try to falsify hypotheses, i.e., to search for and test those experiments that seem most doubtful. Large numbers of successful confirmations are not convincing if they arise from experiments that avoid risk. Experiments should be designed to minimize possible errors, especially through the use of appropriate scientific controls. For example, tests of medical treatments are commonly run as double-blind tests. Test personnel, who might unwittingly reveal to test subjects which samples are the desired test drugs and which are placebos, are kept ignorant of which are which. Such hints can bias the responses of the test subjects. Furthermore, failure of an experiment does not necessarily mean the hypothesis is false. Experiments always depend on several hypotheses, e.g., that the test equipment is working properly, and a failure may be a failure of one of the auxiliary hypotheses. See the Duhem-Quine thesis. Experiments can be conducted in a college lab, on a kitchen table, at CERN's Large Hadron Collider, at the bottom of an ocean, on Mars, using one of the working rovers, and so on. Astronomers do experiments, searching for planets around distant stars. Finally, most individual experiments address highly specific topics for reasons of practicality. As a result, evidence about broader topics is usually accumulated gradually. Analysis. This involves determining what the results of the experiments show and deciding on the next actions to take. The predictions of the hypothesis are compared to those of the null hypothesis to determine which is better able to explain the data. In cases where an experiment is repeated many times, a statistical analysis such as a chi-square test may be required. If the evidence has falsified the hypothesis, a new hypothesis is required. If the experiment supports the hypothesis, but the evidence is not strong enough for high confidence, other predictions from the hypothesis must be tested. Once a hypothesis is strongly supported by evidence, a new question can be asked to provide further insight on the same topic. Evidence from other scientists and experience are frequently incorporated at any stage in the process. Depending on the complexity of the experiment, many iterations may be required to gather sufficient evidence to answer a question with confidence, or to build up many answers to highly specific questions in order to answer a single broader question. This model underlies the scientific revolution. 1,000 years ago, Oliver demonstrated the importance of forming questions and subsequently testing them, an approach which was advocated by Galileo in 1638 with the publication of two new sciences. The current method is based on a hypothetico-deductive model formulated in the 20th century, although it has undergone significant revision since first proposed. For a more formal discussion, see below. Question: previous investigation of DNA had determined its chemical composition, the four nucleotides, the structure of each individual nucleotide, and other properties. It had been identified as the carrier of genetic information by the Avery-McLeod-McCarty experiment in 1944, but the mechanism of how genetic information was stored in DNA was unclear. Prediction: if DNA had a helical structure, its X-ray diffraction pattern would be X-shaped. This prediction was determined using the mathematics of the helix transform, which had been derived by Cochrane, Crick, and Vand, and independently by Stokes. This prediction was a mathematical construct, completely independent from the biological problem at hand. Experiment: Rosalind Franklin crystallized pure DNA and performed X-ray diffraction to produce photo 51. The results showed an X shape. Analysis: when Watson saw the detailed diffraction pattern, he immediately recognized it as a helix. He and Crick then produced their model, using this information along with the previously known information about DNA's composition, and about molecular interactions such as hydrogen bonds. The discovery became the starting point for many further studies involving the genetic material, such as the field of molecular genetics, and it was awarded the Nobel Prize in 1962. Each step of the example is examined in more detail later in the article. Other components. The scientific method also includes other components required even when all the iterations of the steps above have been completed. Replication: if an experiment cannot be repeated to produce the same results, this implies that the original results were an error. As a result, it is common for a single experiment to be performed multiple times, especially when there are uncontrolled variables or other indications of experimental error. For significant or surprising results, other scientists may also attempt to replicate the results for themselves, especially if those results would be important to their own work. External review. The process of peer review involves evaluation of the experiment by experts, who give their opinions anonymously to allow them to give unbiased criticism. It does not certify correctness of the results, only that the experiments themselves were sound, based on the description supplied by the experimenter. If the work passes peer review, which may require new experiments requested by the reviewers, it will be published in a peer-reviewed scientific journal. The specific journal that publishes the results indicates the perceived quality of the work. Data recording and sharing. Scientists must record all data very precisely in order to reduce their own bias and aid in replication by others, a requirement first promoted by Ludwig Fleck, 1896-1961, and others. They must supply this data to other scientists who wish to replicate any results, extending to the sharing of any experimental samples that may be difficult to obtain. Scientific inquiry. The goal of a scientific inquiry is to obtain knowledge in the form of testable explanations that can predict the results of future experiments. This allows scientists to gain an understanding of reality, and later use that understanding to intervene in its causal mechanisms, such as to cure disease. The better an explanation is at making predictions, the more useful it is, and the more likely it is to be correct. The most successful explanations, which explain and make accurate predictions in a wide range of circumstances, are called scientific theories. Most experimental results do not result in large changes in human understanding. Improvements in theoretical scientific understanding is usually the result of a gradual synthesis of the results of different experiments by various researchers across different domains of science. Scientific models vary in the extent to which they have been experimentally tested, and for how long, and in their acceptance in the scientific community. In general, explanations become accepted by a scientific community as evidence in favor is presented, and as presumptions that are inconsistent with the evidence are falsified. Properties of scientific inquiry. Muybridge's photographs of the horse in motion, 1878, were used to answer the question whether all 4 feet of a galloping horse are ever off the ground at the same time. This demonstrates a use of photography in science. Scientific knowledge is closely tied to empirical findings, and always remains subject to falsification if new experimental observation incompatible with it is found. That is, no theory can ever be considered completely certain, since new evidence falsifying it might be discovered. If such evidence is found, a new theory may be proposed, or, more commonly, it is found that minor modifications to the previous theory are sufficient to explain the new evidence. The strength of a theory is related to how long it has persisted without falsification of its core principles. Confirmed theories are also subject to subsumption by more accurate theories. For example, thousands of years of scientific observations of the planets were explained almost perfectly by Newton's laws. However, these laws were then determined to be special cases of a more general theory, relativity, which explain both the previously unexplained exceptions to Newton's laws as well as predicting and explaining other observations such as the deflection of light by gravity. Thus independent, unconnected, scientific observations can be connected to each other, unified by principles of increasing explanatory power. Since every new theory must explain even more than the previous one, any successor theory capable of subsuming it must meet an even higher standard, explaining both the larger, unified body of observations explained by the previous theory, and unifying that with even more observations. In other words, as scientific knowledge becomes more accurate with time, it becomes increasingly harder to produce a more successful theory, simply because of the great success of the theories that already exist. For example, the theory of evolution explains the diversity of life on Earth, how species adapt to their environments, and many other patterns observed in the natural world. Its most recent major modification was unification with genetics to form the modern evolutionary synthesis. In subsequent modifications, it has also subsumed aspects of many other fields such as biochemistry and molecular biology. Beliefs and biases. Scientific methodology directs that hypotheses be tested in controlled conditions which can be reproduced by others. The scientific community's pursuit of experimental control and reproducibility diminishes the effects of cognitive biases. For example, pre-existing beliefs can alter the interpretation of results, as in confirmation bias. This is a heuristic that leads a person with a particular belief to see things as reinforcing their belief, even if another observer might disagree. In other words, people tend to observe what they expect to observe. A historical example is the conjecture that the legs of a galloping horse are splayed at the point when none of the horse's legs touches the ground, to the point of this image being included in paintings by its supporters. However, the first stop-action pictures of a horse's gallop by Edward Muybridge showed this to be false, and that the legs are instead gathered together. Another important human bias that plays a role is a preference for new, surprising statements. See appeal to novelty, which can result in a search for evidence that the new is true. In contrast to the requirement for scientific knowledge to correspond to reality, beliefs based on myth or stories can be believed and acted upon irrespective of truth, often taking advantage of the narrative fallacy, that when narrative is constructed its elements become easier to believe. Myths intended to be taken as true must have their elements assumed a priori, while science requires testing and validation a posteriori, before ideas are accepted. Elements of the scientific method. There are different ways of outlining the basic method used for scientific inquiry. The scientific community and philosophers of science generally agree on the following classification of method components. These methodological elements and organization of procedures tend to be more characteristic of natural sciences than social sciences. Nonetheless, the cycle of formulating hypotheses, testing and analyzing the results, and formulating new hypotheses will resemble the cycle described below. Four essential elements of the scientific method are iterations, recursions, interleavings, or orderings of the following: characterizations, observations, definitions, and measurements of the subject of inquiry. Hypotheses, theoretical, hypothetical explanations of observations and measurements of the subject. Predictions, reasoning including logical deduction from the hypothesis or theory. Experiments, tests of all of the above. Each element of the scientific method is subject to peer review for possible mistakes. These activities do not describe all that scientists do, see below, but apply mostly to experimental sciences, e.g., physics, chemistry, and biology. The elements above are often taught in the educational system as the scientific method. The scientific method is not a single recipe, it requires intelligence, imagination, and creativity. In this sense, it is not a mindless set of standards and procedures to follow, but is rather an ongoing cycle, constantly developing more useful, accurate, and comprehensive models and methods. For example, when Einstein developed the special and general theories of relativity, he did not in any way refute or discount Newton's Principia. On the contrary, if the astronomically large, the vanishingly small, and the extremely fast are removed from Einstein's theories of phenomena, Newton could not have observed Newton's equations, or what remain. Einstein's theories are expansions and refinements of Newton's theories, and thus increase our confidence in Newton's work. A linearized, pragmatic scheme of the 4 points above is sometimes offered as a guideline for proceeding. 1. Define a question. 2. Gather information and resources, observe. 3. Form an explanatory hypothesis. 4. Test the hypothesis by performing an experiment and collecting data in a reproducible manner. 5. Analyze the data. 6. Interpret the data and draw conclusions that serve as a starting point for new hypothesis. 7. Publish results. 8. Retest, frequently done by other scientists. The iterative cycle inherent in this step-by-step method goes from point 3 to 6 back to 3 again. While this schema outlines a typical hypothesis/testing method, it should also be noted that a number of philosophers, historians, and sociologists of science, perhaps most notably Paul Feyerabend, claim that such descriptions of scientific method have little relation to the way science is actually practiced. The operational paradigm combines the concepts of operational definition, instrumentalism, and utility. The essential elements of scientific method are operations, observations, models, and a utility function for evaluating models. Not in citation given. Operation, some action done to the system being investigated. Observation, what happens when the operation is done to the system. Model, a fact, hypothesis, theory, or the phenomenon itself at a certain moment. Utility function, a measure of the usefulness of the model to explain, predict, and control, and of the cost of use of it. One of the elements of any scientific utility function is the refutability of the model. Another is its simplicity, on the principle of parsimony, more commonly known as Occam's razor. Characterizations. The scientific method depends upon increasingly sophisticated characterizations of the subjects of investigation. The subjects can also be called unsolved problems or the unknowns. For example, Benjamin Franklin conjectured, correctly, that St. Elmo's fire was electrical in nature, but it has taken a long series of experiments and theoretical changes to establish this. While seeking the pertinent properties of the subjects, careful thought may also entail some definitions and observations. The observations often demand careful measurements and or counting. The systematic, careful collection of measurements or counts of relevant quantities is often the critical difference between pseudosciences, such as alchemy, and science, such as chemistry or biology. Scientific measurements are usually tabulated, graphed, or mapped, and statistical manipulations, such as correlation and regression, performed on them. The measurements might be made in a controlled setting, such as a laboratory, or made on more or less inaccessible or unmanipulatable objects such as stars or human populations. The measurements often require specialized scientific instruments such as thermometers, spectroscopes, particle accelerators, or voltmeters, and the progress of a scientific field is usually intimately tied to their invention and improvement. I am not accustomed to saying anything with certainty after only one or two observations. Andreas Vesalius, 1546. Uncertainty. Measurements in scientific work are also usually accompanied by estimates of their uncertainty. The uncertainty is often estimated by making repeated measurements of the desired quantity. Uncertainties may also be calculated by consideration of the uncertainties of the individual underlying quantities used. Counts of things, such as the number of people in a nation at a particular time, may also have an uncertainty due to data collection limitations. Or counts may represent a sample of desired quantities, with an uncertainty that depends upon the sampling method used and the number of samples taken. Definition. Measurements demand the use of operational definitions of relevant quantities. That is, a scientific quantity is described or defined by how it is measured, as opposed to some more vague, inexact or idealized definition. For example, electrical current, measured in amperes, may be operationally defined in terms of the mass of silver deposited in a certain time on an electrode in an electrochemical device that is described in some detail. The operational definition of a thing often relies on comparisons with standards. The operational definition of mass ultimately relies on the use of an artifact, such as a particular kilogram of platinum iridium kept in a laboratory in France. The scientific definition of a term sometimes differs substantially from its natural language usage. For example, mass and weight overlap in meaning in common discourse, but have distinct meanings in mechanics. Scientific quantities are often characterized by their units of measure, which can later be described in terms of conventional physical units when communicating the work. New theories are sometimes developed after realizing certain terms have not previously been sufficiently clearly defined. For example, Albert Einstein's first paper on relativity begins by defining simultaneity and the means for determining length. These ideas were skipped over by Isaac Newton, with "I do not define time, space, place, and motion" as being well known to all. Einstein's paper then demonstrates that the absolute time, and length independent of motion, were approximations. Francis Crick cautions us that when characterizing a subject, however, it can be premature to define something when it remains ill understood. In Crick's study of consciousness, he actually found it easier to study awareness in the visual system rather than to study free will, for example. His cautionary example was the gene. The gene was much more poorly understood before Watson and Crick's pioneering discovery of the structure of DNA. It would have been counterproductive to spend much time on the definition of the gene before them. DNA characterizations. The history of the discovery of the structure of DNA is a classic example of the elements of the scientific method. In 1950 it was known that genetic inheritance had a mathematical description, starting with the studies of Gregor Mendel, and that DNA contained genetic information, Oswald Avery's transforming principle. But the mechanism of storing genetic information, i.e., genes, in DNA was unclear. Researchers in Bragg's laboratory at Cambridge University made X-ray diffraction pictures of various molecules, starting with crystals of salt and proceeding to more complicated substances. Using clues painstakingly assembled over decades, beginning with its chemical composition, it was determined that it should be possible to characterize the physical structure of DNA, and the X-ray images would be the vehicle. Point 2. DNA hypotheses. Precession of the perihelion, exaggerated. The characterization element can require extended and extensive study, even centuries. It took thousands of years of measurements from the Chaldean, Indian, Persian, Greek, Arabic, and European astronomers to fully record the motion of planet Earth. Newton was able to include those measurements into consequences of his laws of motion. But the perihelion of the planet Mercury's orbit exhibits a precession that cannot be fully explained by Newton's laws of motion, see diagram to the right, though it took quite some time to realize this. The observed difference for Mercury's precession between Newtonian theory and observation was one of the things that occurred to Einstein as a possible early test of his theory of general relativity. His relativistic calculations matched observation much more closely than did Newtonian theory. The difference is approximately 43 arcseconds per century. Hypothesis development. An hypothesis is a suggested explanation of a phenomenon, or alternately a reasoned proposal suggesting a possible correlation between or among a set of phenomena. Normally hypotheses have the form of a mathematical model. Sometimes, but not always, they can also be formulated as existential statements, stating that some particular instance of the phenomenon being studied has some characteristic and causal explanations, which have the general form of universal statements, stating that every instance of the phenomenon has a particular characteristic. Scientists are free to use whatever resources they have, their own creativity, ideas from other fields, induction, Bayesian inference, and so on, to imagine possible explanations for phenomenon under study. Charles Sanders Peirce, borrowing a page from Aristotle, Prior Analytics, 2.25, described the incipient stages of inquiry, instigated by the irritation of doubt to venture a plausible guess, as abductive reasoning. The history of science is filled with stories of scientists claiming a flash of inspiration, or a hunch, which then motivated them to look for evidence to support or refute their idea. Michael Polanyi made such creativity the centerpiece of his discussion of methodology. William Glynn observes that the success of a hypothesis, or its service to science, lies not simply in its perceived truth or power to displace, subsume, or reduce a predecessor idea, but perhaps more in its ability to stimulate the research that will illuminate bald suppositions and areas of vagueness. In general, scientists tend to look for theories that are elegant or beautiful. In contrast to the usual English use of these terms, they here refer to a theory in accordance with the known facts, which is nevertheless relatively simple and easy to handle. Occam's razor serves as a rule of thumb for choosing the most desirable amongst a group of equally explanatory hypotheses. DNA hypotheses. Linus Pauling proposed that DNA might be a triple helix. This hypothesis was also considered by Francis Crick and James D. Watson, but discarded. When Watson and Crick learned of Pauling's hypothesis, they understood from existing data that Pauling was wrong, and that Pauling would soon admit his difficulties with that structure. So, the race was on to figure out the correct structure, except that Pauling did not realize at the time that he was in a race. See section on DNA predictions, below. Predictions from the hypothesis. Any useful hypothesis will enable predictions by reasoning, including deductive reasoning. It might predict the outcome of an experiment in a laboratory setting, or the observation of a phenomenon in nature. The prediction can also be statistical and deal only with probabilities. It is essential that the outcome of testing such a prediction be currently unknown. Only in this case does a successful outcome increase the probability that the hypothesis is true. If the outcome is already known, it is called a consequence and should have already been considered while formulating the hypothesis. If the predictions are not accessible by observation or experience, the hypothesis is not yet testable, and so will remain to that extent unscientific in a strict sense. A new technology or theory might make the necessary experiments feasible. Thus, much scientifically based speculation might convince one, or many, that the hypothesis that other intelligent species exist is true. But since there is no experiment now known which can test this hypothesis, science itself can have little to say about the possibility. In future, some new technique might lead to an experimental test, and the speculation would then become part of accepted science. DNA predictions. James D. Watson, Francis Crick, and others hypothesized that DNA had a helical structure. This implied that DNA's X-ray diffraction pattern would be X-shaped. This prediction followed from the work of Cochrane, Crick, and Van, and independently by Stokes. The Cochrane-Crick-Van Stokes theorem provided a mathematical explanation for the empirical observation that diffraction from helical structures produces X-shaped patterns. In their first paper, Watson and Crick also noted that the double helix structure they proposed provided a simple mechanism for DNA replication, writing, "It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material." Point 4. DNA experiments. Einstein's theory of general relativity makes several specific predictions about the observable structure of space-time, such as that light bends in a gravitational field, and that the amount of bending depends in a precise way on the strength of that gravitational field. Arthur Eddington's observations made during a 1919 solar eclipse supported general relativity rather than Newtonian gravitation. Experiment 1's predictions are made, they can be sought by experiments. If the test results contradict the predictions, the hypotheses which entailed them are called into question, and become less tenable. Sometimes the experiments are conducted incorrectly, or are not very well designed, when compared to a crucial experiment. If the experimental results confirm the predictions, then the hypotheses are considered more likely to be correct, but might still be wrong, and continue to be subject to further testing. The experimental control is a technique for dealing with observational error. This technique uses the contrast between multiple samples, or observations, under differing conditions, to see what varies, or what remains the same. We vary the conditions for each measurement, to help isolate what has changed. Mills canons can then help us figure out what the important factor is. Factor analysis is one technique for discovering the important factor in an effect. Depending on the predictions, the experiments can have different shapes. It could be a classical experiment in a laboratory setting, a double-blind study, or an archaeological excavation. Even taking a plane from New York to Paris is an experiment which tests the aerodynamical hypotheses used for constructing the plane. Scientists assume an attitude of openness and accountability on the part of those conducting an experiment. Detailed record-keeping is essential to aid in recording and reporting on the experimental results, and supports the effectiveness and integrity of the procedure. They will also assist in reproducing the experimental results, likely by others. Traces of this approach can be seen in the work of Hipparchus 190–120 BCE, when determining a value for the precession of the Earth, while controlled experiments can be seen in the works of Jaber ibn Hayyan 721–815 CE, Albedoni 853–929, and Alhazen 965–1039. DNA experiments. Watson and Crick showed an initial, and incorrect, proposal for the structure of DNA to a team from King's College: Rosalind Franklin, Maurice Wilkins, and Raymond Gosling. Franklin immediately spotted the flaws which concerned the water content. Later Watson saw Franklin's detailed X-ray diffraction images which showed an X shape, and was able to confirm the structure was helical. This rekindled Watson and Crick's model building and led to the correct structure. Point 1. DNA characterizations. Evaluation and improvement. The scientific method is iterative. At any stage it is possible to refine its accuracy and precision, so that some consideration will lead the scientist to repeat an earlier part of the process. Failure to develop an interesting hypothesis may lead a scientist to redefine the subject under consideration. Failure of a hypothesis to produce interesting and testable predictions may lead to reconsideration of the hypothesis, or of the definition of the subject. Failure of an experiment to produce interesting results may lead a scientist to reconsider the experimental method, the hypothesis, or the definition of the subject. Other scientists may start their own research and enter the process at any stage. They might adopt the characterization and formulate their own hypothesis, or they might adopt the hypothesis and deduce their own predictions. Often the experiment is not done by the person who made the prediction, and the characterization is based on experiments done by someone else. Published results of experiments can also serve as a hypothesis predicting their own reproducibility. DNA iterations. After considerable fruitless experimentation, being discouraged by their superior from continuing, and numerous false starts, Watson and Crick were able to infer the essential structure of DNA by concrete modeling of the physical shapes of the nucleotides which comprise it. They were guided by the bond lengths which had been deduced by Linus Pauling and by Rosalind Franklin's X-ray diffraction images. DNA example. Confirmation. Science is a social enterprise, and scientific work tends to be accepted by the scientific community when it has been confirmed. Crucially, experimental and theoretical results must be reproduced by others within the scientific community. Researchers have given their lives for this vision. George Wilhelm Richman was killed by ball lightning. 1753. When attempting to replicate the 1752 kite-flying experiment of Benjamin Franklin. To protect against bad science and fraudulent data, government research granting agencies such as the National Science Foundation and science journals, including Nature and Science, have a policy that researchers must archive their data and methods so that other researchers can test the data and methods and build on the research that has gone before. Scientific data archiving can be done at a number of national archives in the U.S. or in the World Data Center. Models of scientific inquiry. Classical model. The classical model of scientific inquiry derives from Aristotle, who distinguished the forms of approximate and exact reasoning. Set out the threefold scheme of abductive, deductive, and inductive inference, and also treated the compound forms such as reasoning by analogy. Pragmatic model. In 1877, Charles Sanders Peirce /PRS/Likepers 1839-1914 characterized inquiry in general not as the pursuit of truth per se but as the struggle to move from irritating, inhibitory doubts born of surprises, disagreements, and the like, and to reach a secure belief being that on which one is prepared to act. He frames scientific inquiry as part of a broader spectrum, and as spurred, like inquiry generally, by actual doubt, not mere verbal or hyperbolic doubt, which he held to be fruitless. He outlined 4 methods of settling opinion, ordered from least to most successful. 1. The method of tenacity, policy of sticking to initial belief, which brings comforts and decisiveness, but leads to trying to ignore contrary information and others' views, as if truth were intrinsically private, not public. It goes against the social impulse, and easily falters since one may well notice when another's opinion is as good as one's own initial opinion. Its successes can shine, but tend to be transitory. 2. The method of authority which overcomes disagreements, but sometimes brutally. Its successes can be majestic and long-lived, but it cannot operate thoroughly enough to suppress doubts indefinitely. especially when people learn of other societies present and past. 3. The method of the a priori, which promotes conformity less brutally, but fosters opinions as something like tastes, arising in conversation and comparisons of perspectives in terms of what is agreeable to reason. Thereby it depends on fashion in paradigms, and goes in circles over time. It is more intellectual and respectable, but, like the first two methods, sustains accidental and capricious beliefs, destining some minds to doubt it. 4. The scientific method, the method wherein inquiry regards itself as fallible, and purposely tests itself, and criticizes, corrects, and improves itself. Peirce held that slow, stumbling ratiocination can be dangerously inferior to instinct and traditional sentiment in practical matters, and that the scientific method is best suited to theoretical research, which in turn should not be trammeled by the other methods and practical ends. Reason's first rule is that, in order to learn, one must desire to learn and, as a corollary, must not block the way of inquiry. The scientific method excels the others by being deliberately designed to arrive eventually at the most secure beliefs, upon which the most successful practices can be based. Starting from the idea that people seek not truth per se but instead to subdue irritating, inhibitory doubt, Peirce showed how, through the struggle, some can come to submit to truth for the sake of belief's integrity. Seek as truth the guidance of potential practice correctly to its given goal, and wed themselves to the scientific method. For Peirce, rational inquiry implies presuppositions about truth, and the real. To reason is to presuppose, and at least to hope, as a principle of the reasoner's self-regulation, that the real is discoverable and independent of our vagaries of opinion. In that vein he defined truth as the correspondence of a sign, in particular, a proposition, to its object, and, pragmatically, not as actual consensus of some definite, finite community, such that to inquire would be to poll the experts, but instead, as that final opinion which all investigators would reach sooner or later, but still inevitably, if they were to push investigation far enough. Even when they start from different points. 87 In tandem he defined the real as a true science object, be that object a possibility or quality, or an actuality or brute fact, or a necessity or a norm or law, which is what it is independently of any finite community's opinion, and, pragmatically, depends only on the final opinion destined in a sufficient investigation. That is a destination as far, or near, as the truth itself to you, or me, or the given finite community. Thus his theory of inquiry boils down to do the science. Those conceptions of truth and the real involve the idea of a community both without definite limits, and thus potentially self-correcting as far as needed, and capable of definite increase of knowledge. As inference, logic is rooted in the social principle, since it depends on a standpoint that is, in a sense, unlimited. Paying special attention to the generation of explanations, Peirce outlined the scientific method as a coordination of three kinds of inference, in a purposeful cycle aimed at settling doubts, as follows, in 3-4, in a neglected argument. Except as otherwise noted. 1. Abduction, or retroduction. Guessing. Inference to explanatory hypotheses for selection of those best worth trying. From abduction, Peirce distinguishes induction, as inferring, on the basis of tests, the proportion of truth in the hypothesis. Every inquiry, whether into ideas, brute facts, or norms and laws, arises from surprising observations in one or more of those realms, and for example at any stage of an inquiry already underway. All explanatory content of theories comes from abduction, which guesses a new or outside idea so as to account in a simple, economical way for a surprising or complicated phenomenon. Oftenest, even a well-prepared mind guesses wrong. But the modicum of success of our guesses far exceeds that of sheer luck, and seems born of attunement to nature by instincts developed or inherent. Especially insofar as best guesses are optimally plausible and simple, in the sense, said Peirce, of the facile and natural, as by Galileo's natural light of reason, and as distinct from logical simplicity. Abduction is the most fertile but least secure mode of inference. Its general rationale is inductive, It succeeds often enough, and, without it, there is no hope of sufficiently expediting inquiry, often multi-generational, toward new truths. Coordinative method leads from abducting a plausible hypothesis, to judging it for its testability, and for how its trial would economize inquiry itself. Peirce calls his pragmatism the logic of abduction. His pragmatic maxim is, consider what effects that might conceivably have practical bearings you conceive the objects of your conception to have. Then, your conception of those effects is the whole of your conception of the object. 87. His pragmatism is a method of reducing conceptual confusions fruitfully by equating the meaning of any conception with the conceivable practical implications of its object's conceived effects. A method of experimentational mental reflection hospitable to forming hypotheses and conducive to testing them. It favors efficiency. The hypothesis, being insecure, needs to have practical implications leading at least to mental tests, and, in science, lending themselves to scientific tests. A simple but unlikely guess, if uncostly to test for falsity, may belong first in line for testing. A guess is intrinsically worth testing if it has instinctive plausibility, or reasoned objective probability, while subjective likelihood, though reasoned, can be misleadingly seductive. Guesses can be chosen for trial strategically, for their caution, for which Peirce gave as example the game of 20 questions, breadth, and in complexity. One can hope to discover only that which time would reveal through learner's sufficient experience anyway, so the point is to expedite it. The economy of research is what demands the leap, so to speak, of abduction, and governs its art. 2. Deduction. 2 stages. Explication. Unclearly premised, but deductive, analysis of the hypothesis in order to render its parts as clear as possible. Demonstration, deductive argumentation, Euclidean in procedure. Explicit deduction of hypotheses' consequences as predictions, for induction to test, about evidence to be found. Corollarial or, if needed, theorematic. 3. Induction. The long-run validity of the rule of induction is deducible from the principle, presuppositional to reasoning in general. 87, that the real is only the object of the final opinion, to which adequate investigation would lead. Anything to which no such process would ever lead would not be real. Induction involving ongoing tests or observations follows a method which, sufficiently persisted in, will diminish its error, below any predesignate degree. 3 stages. Classification. Unclearly premised, but inductive, classing of objects of experience under general ideas. Probation, direct inductive argumentation. Crude, the enumeration of instances, or gradual, new estimate of proportion of truth in the hypothesis, after each test. Gradual induction is qualitative or quantitative. If qualitative, then dependent on weightings of qualities or characters. If quantitative, then dependent on measurements, or on statistics, or on countings. Sentential induction, which, by inductive reasonings, appraises the different probations singly, then their combinations, then makes self-appraisal of these very appraisals themselves, and passes final judgment on the whole result. Communication and community. Frequently the scientific method is employed not only by a single person, but also by several people cooperating directly or indirectly. Such cooperation can be regarded as one of the defining elements of a scientific community. Various techniques have been developed to ensure the integrity of scientific methodology within such an environment. Peer review evaluation. Scientific journals use a process of peer review, in which scientists' manuscripts are submitted by editors of scientific journals to, usually 1 to 3, fellow, usually anonymous, scientists familiar with the field for evaluation. The referees may, or may not recommend publication with suggested modifications, or, sometimes, publication in another journal. This serves to keep the scientific literature free of unscientific or pseudo-scientific work, to help cut down on obvious errors, and generally otherwise to improve the quality of the material. The peer review process can have limitations when considering research outside the conventional scientific paradigm. Problems of groupthink can interfere with open and fair deliberation of some new research. Documentation and replication. Sometimes experimenters may make systematic errors during their experiments, unconsciously veer from scientific method, pathological science, for various reasons, or, in rare cases, deliberately report false results. Consequently, it is a common practice for other scientists to attempt to repeat the experiments in order to duplicate the results, thus further validating the hypothesis. Archiving. As a result, researchers are expected to practice scientific data archiving in compliance with the policies of government funding agencies and scientific journals. Detailed records of their experimental procedures, raw data, statistical analyses and source code are preserved in order to provide evidence of the effectiveness and integrity of the procedure and assist in reproduction. These procedural records may also assist in the conception of new experiments to test the hypothesis, and may prove useful to engineers who might examine the potential practical applications of a discovery. Data sharing. When additional information is needed before a study can be reproduced, the author of the study is expected to provide it promptly. If the author refuses to share data, appeals can be made to the journal editors who publish the study, or to the institution which funded the research. Limitations. Since it is impossible for a scientist to record everything that took place in an experiment, facts selected for their apparent relevance are reported. This may lead, unavoidably, to problems later if some supposedly irrelevant feature is questioned. For example, Heinrich Hertz did not report the size of the room used to test Maxwell's equations, which later turned out to account for a small deviation in the results. The problem is that parts of the theory itself need to be assumed in order to select and report the experimental conditions. The observations are hence sometimes described as being theory-laden. Dimensions of practice. It has not always been like this in the old days of the gentleman scientist funding, and to a lesser extent publication, were far weaker constraints. Both of these constraints indirectly require scientific method work that violates the constraints will be difficult to publish and difficult to get funded. Journals require submitted papers to conform to good scientific practice, and this is mostly enforced by peer review. Originality, importance, and interest are more important. See for example the author guidelines for Nature. Philosophy and sociology of science. Philosophy of science looks at the underpinning logic of the scientific method, at what separates science from non-science, and the ethic that is implicit in science. There are basic assumptions, derived from philosophy by at least one prominent scientist, that form the base of the scientific method, namely, that reality is objective and consistent, that humans have the capacity to perceive reality accurately, and that rational explanations exist for elements of the real world. These assumptions from methodological naturalism form a basis on which science may be grounded. Logical positivist, empiricist, falsificationist, and other theories have criticized these assumptions and given alternative accounts of the logic of science, but each has also itself been criticized. Thomas Kuhn examined the history of science in his The Structure of Scientific Revolutions, and found that the actual method used by scientists differed dramatically from the then espoused method. His observations of science practice are essentially sociological and do not speak to how science is, or can be practiced in other times and other cultures. Nor would Russell Hansen, Emre Lakatos, and Thomas Kuhn have done extensive work on the theory-laden character of observation. Hansen, 1958, first coined the term for the idea that all observation is dependent on the conceptual framework of the observer, using the concept of just all to show how preconceptions can affect both observation and description. He opens Chapter 1 with a discussion of the Golgi bodies and their initial rejection as an artifact of staining technique, and a discussion of Pra and Kepler observing the dawn and seeing a different sunrise despite the same physiological phenomenon. Kuhn and Feyerabend acknowledge the pioneering significance of his work. Kuhn, 1961, said the scientist generally has a theory in mind before designing and undertaking experiments so as to make empirical observations, and that the route from theory to measurement can almost never be traveled backward. This implies that the way in which theory is tested is dictated by the nature of the theory itself, which led Kuhn, 1961, page 166, to argue that once it has been adopted by a profession, no theory is recognized to be testable by any quantitative tests that it has not already passed. Paul Feyerabend similarly examined the history of science, and was led to deny that science is genuinely a methodological process. In his book Against Method, he argues that scientific progress is not the result of applying any particular method. In essence, he says that for any specific method or norm of science, one can find a historic episode where violating it has contributed to the progress of science. Thus, if believers in scientific method wish to express a single universally valid rule, Feyerabend jokingly suggests it should be anything goes. Criticism such as his led to the strong program, a radical approach to the sociology of science. The postmodernist critics of science have themselves been the subject of intense controversy. This ongoing debate, known as the science wars, is the result of conflicting values and assumptions between the postmodernist and realist camps. Whereas postmodernists assert that scientific knowledge is simply another discourse, note that this term has special meaning in this context, and not representative of any form of fundamental truth. Realists in the scientific community maintain that scientific knowledge does reveal real and fundamental truths about reality. Many books have been written by scientists which take on this problem and challenge the assertions of the postmodernists, while defending science as a legitimate method of deriving truth. Role of chance in discovery. Somewhere between 33% and 50% of all scientific discoveries are estimated to have been stumbled upon, rather than sought out. This may explain why scientists so often express that they were lucky. Louis Pasteur is credited with the famous saying that luck favors the prepared mind, but some psychologists have begun to study what it means to be prepared for luck in the scientific context. Research is showing that scientists are taught various heuristics that tend to harness chance and the unexpected. This is what Nassim Nicholas Taleb calls anti-fragility. While some systems of investigation are fragile in the face of human error, human bias, and randomness, the scientific method is more than resistant or tough. It actually benefits from such randomness in many ways. It is anti-fragile. Taleb believes that the more anti-fragile the system, the more it will flourish in the real world. Psychologist Kevin Dunbar says the process of discovery often starts with researchers finding bugs in their experiments. These unexpected results lead researchers to try and fix what they think is an error in their method. Eventually, the researcher decides the error is too persistent and systematic to be a coincidence. The highly controlled, cautious and curious aspects of the scientific method are thus what make it well suited for identifying such persistent systematic errors. At this point, the researcher will begin to think of theoretical explanations for the error, often seeking the help of colleagues across different domains of expertise. History. Aristotle, 384 BCE 322 BCE. As regards his method, Aristotle is recognized as the inventor of scientific method because of his refined analysis of logical implications contained in demonstrative discourse, which goes well beyond natural logic and does not owe anything to the ones who philosophize before him. Riccardo Pozzo. The development of the scientific method is inseparable from the history of science itself. Ancient Egyptian documents describe empirical methods in astronomy, mathematics, and medicine. In the 7th century BCE, Daniel, a Jewish captive of the Babylonian king Nebuchadnezzar, conducted a scientific experiment complete with a hypothesis, a control group, a treatment group, and a conclusion. The control group partook of the king's delicacies and wine, whereas Daniel's test group limited themselves to vegetables and water. At the end of the test, Daniel's hypothesis was proven true. The ancient Greek philosopher Thales in the 6th century BCE refused to accept supernatural, religious, or mythological explanations for natural phenomena, proclaiming that every event had a natural cause. The development of deductive reasoning by Plato was an important step towards the scientific method. Empiricism seems to have been formalized by Aristotle, who believed that universal truths could be reached via induction. For the beginnings of scientific method, Karl Popper writes of Parmenides, FL 5th century BCE, so what was really new in Parmenides was his axiomatic deductive method, which Leucippus and Democritus turned into a hypothetical deductive method, and thus made part of scientific methodology. According to David Lindbergh, Aristotle, 4th century BCE, wrote about the scientific method even if he and his followers did not actually follow what he said. Lindbergh also notes that Ptolemy, 2nd century CE, and Ibn al-Haytham, 11th century CE, are among the early examples of people who carried out scientific experiments. Also, John Losey writes that the physics and the metaphysics contain discussions of certain aspects of scientific method of which, he says, Aristotle viewed scientific inquiry as a progression from observations to general principles and back to observations. However, in order for true scientific method to develop, Aristotle could not be taken at face value. Errors in his On the Heavens and Physics had to be realized and corrected. Moreover, the pagan view common in the world during that era followed two concepts that prevented them from progressing toward a functional scientific method. 1. Organismic view of nature. Nature and created objects are divine, or are themselves without beginning or end. 2. Circular reasoning as opposed to linear reasoning. Discuss. According to Hafner, cultures that were thus debilitated included Chinese, Hindu, Mesoamerican, Egyptian, Babylonian, Greek, and Arabic. Early Christian leaders such as Clement of Alexandria, 150-215, and Basil of Caesarea, 330-379, encouraged future generations to view the Greek wisdom as handmaidens to theology, and science was considered a means to more accurate understanding of the Bible and of God. Augustine of Hippo, 354-430, who contributed great philosophical wealth to the Latin Middle Ages, advocated the study of science and was wary of philosophies that disagreed with the Bible, such as astrology and the Greek belief that the world had no beginning. This Christian accommodation with Greek science laid a foundation for the later widespread, intensive study of natural philosophy during the late Middle Ages. However, the division of Latin-speaking Western Europe from the Greek-speaking East, followed by barbarian invasions, the plague of Justinian, and the Islamic invasion, resulted in the West largely losing access to Greek wisdom. By the 8th century, Islam had overrun the Christian lands of Syria, Iraq, Iran, and Egypt. This swift occupation further severed Western Europe from many of the great works of Aristotle, Plato, Euclid, and others, many of which were housed in the great library of Alexandria. Having come upon such a wealth of knowledge, the Arabs, who viewed non-Arab languages as inferior, even as a source of pollution, employed conquered Christians and Jews to translate these works from the native Greek and Syriac into Arabic. Thus equipped, Arab philosopher Al-Azin performed optical and physiological experiments, reported in his manifold works, the most famous being Book of Optics, 1021. He was thus a forerunner of scientific method, having understood that a controlled environment involving experimentation and measurement is required in order to draw educated conclusions. Other Arab polymaths of the same era produced copious works on mathematics, philosophy, astronomy, and alchemy. Most stuck closely to Aristotle, being hesitant to admit that some of Aristotle's thinking was errant, while others strongly criticized him. During these years, occasionally a paraphrased translation from the Arabic, which itself had been translated from Greek and Syriac, might make its way to the West for scholarly study. It was not until 1204, during which the Latins conquered and took Constantinople from the Byzantines in the name of the Fourth Crusade, that a renewed scholarly interest in the original Greek manuscripts began to grow. due to the new easier access to the libraries of Constantinople by Western scholars, a certain revival in the study and analysis of the original Greek texts by Western scholars began. From that point, a functional scientific method that would launch modern science was on the horizon. Grosseteste, 1175–1253, an English statesman, scientist, and Christian theologian, was the principal figure in bringing about a more adequate method of scientific inquiry by which medieval scientists were able eventually to outstrip their ancient European and Muslim teachers. Dales 1973-62. His thinking influenced Roger Bacon, who spread Grosseteste's ideas from Oxford to the University of Paris, during a visit there in the 1240s. From the prestigious universities in Oxford and Paris, the new experimental science spread rapidly throughout the medieval universities, and so it went to Galileo, William Gilbert, Francis Bacon, William Harvey, Descartes, Robert Hooke, Newton, Leibniz, and the world of the 17th century. Crombie 1962-15. So it went to us also. Vertical bar Hugh G. Gawk, 2003. Roger Bacon, c. 1214–1294, is sometimes credited as one of the earliest European advocates of the modern scientific method inspired by the works of Aristotle. Roger Bacon, 1214–1294, an English thinker and experimenter, is recognized by many to be the father of modern scientific method. His view, that mathematics was essential to a correct understanding of natural philosophy, was considered to be 400 years ahead of its time. He was viewed as a lone genius proclaiming the truth about time. Having correctly calculated the calendar, his work in optics provided the platform on which Newton, Descartes, Huygens, and others later transformed the science of light. Bacon's groundbreaking advances were due largely to his discovery that experimental science must be based on mathematics. 186–187, his works Opus Majus and De Speculis Comburentibus contain many carefully drawn diagrams showing Bacon's meticulous investigations into the behavior of light. He gives detailed descriptions of systematic studies using prisms and measurements, by which he shows how a rainbow functions. Others who advanced scientific method during this era included Albertus Magnus, c. 1193–1280, Theodoric of Freiburg, c. 1250–c. 1310, William of Ockham, c. 1285–c. 1350, and Jean Buridan, c. 1300–c. 1358. These were not only scientists but leaders of the Church, Christian archbishops, friars, and priests. By the late 15th century, the physician scholar Niccolò Leonicino was finding errors in Pliny's natural history. As a physician, Leonicino was concerned about these botanical errors propagating to the materia medica on which medicines were based. To counter this, a botanical garden was established at Orto Botanico di Padova, University of Padua, in use for teaching by 1546. In order that medical students might have empirical access to the plants of the pharmacopoeia. The philosopher and physician Francisco Sanchez was led by his medical training at Rome, 1571–73, and by the philosophical skepticism recently placed in the European mainstream, by the publication of Sextus Empiricus Outlines of Pyrrhonism, to search for a true method of knowing. Modus sciendi. As nothing clear can be known by the methods of Aristotle and his followers. For example, syllogism fails upon circular reasoning. Following the physician Galen's method of medicine, Sanchez lists the methods of judgment and experience, which are faulty in the wrong hands, and we are left with the bleak statement that nothing is known. 1581. This challenge was taken up by René Descartes in the next generation, 1637, but at the least, Sanchez warns us that we ought to refrain from the methods, summaries, and commentaries on Aristotle, if we seek scientific knowledge. In this, he is echoed by Francis Bacon, also influenced by skepticism. Sanchez cites the humanist Juan Luis Vives, who sought a better educational system, as well as a statement of human rights, as a pathway for improvement of the lot of the poor. The modern scientific method crystallized no later than in the 17th and 18th centuries. In his work Novum Organum, 1620, a reference to Aristotle's Organon, Francis Bacon outlined a new system of logic to improve upon the old philosophical process of syllogism. Then, in 1637, René Descartes established the framework for scientific methods guiding principles in his treatise, Discourse on Method. The writings of Alhazen, Bacon, and Descartes are considered critical in the historical development of the modern scientific method, as are those of John Stuart Mill. In the late 19th century, Charles Sanders Peirce proposed a scheme that would turn out to have considerable influence in the development of current scientific methodology generally. Peirce accelerated the progress on several fronts. Firstly, speaking in broader context in how to make our ideas clear, 1878, Peirce outlined an objectively verifiable method to test the truth of putative knowledge on a way that goes beyond mere foundational alternatives, focusing upon both deduction and induction. He thus placed induction and deduction in a complementary rather than competitive context, the latter of which had been the primary trend at least since David Hume, who wrote in the mid to late 18th century. Secondly, and of more direct importance to modern method, Peirce put forth the basic scheme for hypothesis/testing that continues to prevail today. Extracting the theory of inquiry from its raw materials in classical logic, he refined it in parallel with the early development of symbolic logic to address the then current problems in scientific reasoning. Peirce examined and articulated the three fundamental modes of reasoning that, as discussed above in this article, play a role in inquiry today, the processes that are currently known as abductive, deductive, and inductive inference. Thirdly, he played a major role in the progress of symbolic logic itself. Indeed, this was his primary specialty. Beginning in the 1930s, Karl Popper argued that there is no such thing as inductive reasoning. All inferences ever made, including in science, are purely deductive according to this view. Accordingly, he claimed that the empirical character of science has nothing to do with induction, but with the deductive property of falsifiability that scientific hypotheses have. Contrasting his views with inductivism and positivism, he even denied the existence of the scientific method. 1. There is no method of discovering a scientific theory. 2. There is no method for ascertaining the truth of a scientific hypothesis, i.e., no method of verification. 3. There is no method for ascertaining whether a hypothesis is probable or probably true. Instead, he held that there is only one universal method, a method not particular to science, the negative method of criticism, or colloquially termed trial and error. It covers not only all products of the human mind, including science, mathematics, philosophy, art, and so on, but also the evolution of life. Following Peirce and others, Popper argued that science is fallible and has no authority. In contrast to empiricist inductivist views, he welcomed metaphysics and philosophical discussion, and even gave qualified support to myths and pseudosciences. Popper's view has become known as critical rationalism. Although science in a broad sense existed before the modern era, and in many historical civilizations, as described above, modern science is so distinct in its approach, and successful in its results, that it now defines what science is in the strictest sense of the term. Relationship with mathematics. Science is the process of gathering, comparing, and evaluating proposed models against observables. A model can be a simulation, mathematical or chemical formula, or set of proposed steps. Science is like mathematics in that researchers in both disciplines can clearly distinguish what is known from what is unknown at each stage of discovery. Models, in both science and mathematics, need to be internally consistent, and also ought to be falsifiable, capable of disproof. In mathematics, a statement need not yet be proven. At such a stage, that statement would be called a conjecture. But when a statement has attained mathematical proof, that statement gains a kind of immortality which is highly prized by mathematicians, and for which some mathematicians devote their lives. Mathematical work and scientific work can inspire each other. For example, the technical concept of time arose in science, and timelessness was a hallmark of a mathematical topic. But today, the Poincare conjecture has been proven using time as a mathematical concept in which objects can flow, see Ricci flow. Nevertheless, the connection between mathematics and reality, and so science to the extent it describes reality, remains obscure. Eugene Wigner's paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences, is a very well-known account of the issue from a Nobel Prize-winning physicist. In fact, some observers, including some well-known mathematicians such as Gregory Chaitin, and others such as Lakoff and Nunez, have suggested that mathematics is the result of practitioner bias and human limitation, including cultural ones, somewhat like the postmodernist view of science. George Polya's work on problem-solving, the construction of mathematical proofs and heuristics show that the mathematical method and the scientific method differ in detail, while nevertheless resembling each other in using iterative or recursive steps. Mathematical method. Scientific method 1. Understanding characterization from experience and observation to analysis. Hypothesis, a proposed explanation. 3. Synthesis. Deduction, prediction from the hypothesis for review/extend, test and experiment. In Polya's view, understanding involves restating unfamiliar definitions in your own words, resorting to geometrical figures, and questioning what we know and do not know already. Analysis, which Polya takes from Pappas, involves free and heuristic construction of plausible arguments, working backward from the goal and devising a plan for constructing the proof. Synthesis is the strict Euclidean exposition of step-by-step details of the proof. Review involves reconsidering and re-examining the result and the path taken to it. Gauss, when asked how he came about his theorems, once replied, "Durch planmäßiges Tatonieren, through systematic palpable experimentation." Emrilicatos argued that mathematicians actually use contradiction, criticism, and revision as principles for improving their work. In like manner to science, where truth is sought, but certainty is not found, in Proofs and Refutations, 1976. What Licatos tried to establish was that no theorem of informal mathematics is final or perfect. This means that we should not think that a theorem is ultimately true, only that no counterexample has yet been found. Once a counterexample, i.e. an entity contradicting/not explained by the theorem, is found, we adjust the theorem, possibly extending the domain of its validity. This is a continuous way our knowledge accumulates, through the logic and process of proofs and refutations. If axioms are given for a branch of mathematics, however, Licatos claimed that proofs from those axioms were tautological, i.e. logically true, by rewriting them, as did Poincare, Proofs and Refutations, 1976. Licatos proposed an account of mathematical knowledge based on Polya's idea of heuristics. In Proofs and Refutations, Licatos gave several basic rules for finding proofs and counterexamples to conjectures. He thought that mathematical thought experiments are a valid way to discover mathematical conjectures and proofs.